All right, let's look at the variation of parameters. All right, so we have non-homogeneous second-order linear equation here with complementary solution involves y1 and y2. All right, there's a way to cook up the particular solution using y1 and y2. So here's the formula, right? Where W represents the Wronskians of y1 and y2. All right, so let's see if we can derive this formula. All right, so first we're going to look for a particular solution of a specific format, so which is this guy right here. All right, so y sub p is equal to some function u1 times y1 and plus some function u2 times y2, right? So we are trying to find the u1 and u2. Then we have the complete formula, right? So we need the first derivative and the second derivative. So we're going to take the derivative here, right? So if you take the first derivative, we're going to get this, right? And here we're going to make a kind of a crucial, but also kind of a selfish assumption here. All right, so since we have u1 prime and u2 prime, and we have to take another derivative, so we're going to end up having u1 double prime and u2 double prime. And we would rather not deal with the second derivative of u1 and u2. So we're going to make this kind of a selfish assumption that the sum of these two terms is going to be equal to 0. So I'm going to write that down. So it's going to be, let's see, the equation is going to look like this right here. All right, so I'm going to make this assumption here. All right, so I changed the order here, but it's just the sum of these two terms is equal to 0. And I'm going to actually gray those guys out. So here, how about that? All right, so those terms are gone. Right, it's assuming that that's 0. All right, that makes our lives a little bit easier finding second derivative of y sub p, which is going to look like this. All right, it's just a product rule, right? All right, then we have y sub p first prime, and y sub p double prime, and we're going to plug those guys into the original non-homogeneous equation. You're going to end up something like this. All right, so plug them in and doing a little bit of rearranging and factoring out, common factor u1 and u2. All right, you're going to get all these terms. All right, but the good thing is knowing that the y1 and y2 are the solution of the homogeneous equation, we know that this expression right here is going to be 0. And also this expression right here is going to be 0. So we can actually just cancel those guys out. So I'm going to just put, let's see, I'm going to gray those out so that we can still see them. So here, we're going to get something like this. All right, so those guys are gone because those are 0. All right, so we only have those two terms left. And then this is equal to the right-hand side. Right-hand side is f. So I'm going to just call it f here. All right, so here is set that equal to f. All right, so now we have this second equation here. Maybe I'll change the color so we can see it a little bit better here. So I'm going to just change it to maybe a purple or something like that so you can see it better. All right, so we see this second equation here. All right, so I'm going to just write that down. All right, so we have that equation. All right, now, again, I changed the order here, so I put the y1 prime first and the same thing, y2 prime first, but the same equation. All right, so we have a couple of equations. So you have a system of equations involving u1 prime and a u2 prime. All right, so I'm going to borrow a little bit or two from linear algebra. So I'm going to turn this into a matrix equation. So which is going to look something like this. All right, so here, if you multiply it out, so row times column, you're going to get the first equation. and second row times column gives you the second equation. So it's equivalent equation. It's just in matrix form. All right. Then, since we're looking for U1 and U2, first we're going to try to find U1 prime and U2 prime. Right, we can solve this matrix equation by simply multiply both sides by the inverse matrix of the coefficient matrix here. So why don't we do that? So we can write it this way here. Right, so we have. Alright, so we multiply both sides of the equation by the inverse matrix. So this is gone. So you have U1 prime, U2 prime. And then you have an inverse there. And then right hand side is 0 and F. Right? So using the formula of inverse matrix of 2 by 2 matrix, right, we know that the inverse is 1 over determinant of the matrix. And we switch in these two guys and then put a negative sign on those. All right, so we have inverse matrix, which looks like this. All right, and luckily, all right, so it's a 1 over determinant of this matrix. But the determinant of this matrix is exactly the same thing as the Wronskian of y1 and y2. So it's going to be 1 over Wronskian. Right, and I'm going to switch y1 and y2 prime. So y2 prime goes up here, y1, and then putting a negative sign on those. So negative y2 and negative y1 prime, and then 0 and F. And if you multiply it out, you're going to end up something like this. All right, so we're going to get this guy right here. All right, just row times column, and then divide by Wronskians. We get those. All right, so we know that the U1 prime, we have this, and we know U2 prime comes out to be this. But we're looking for U1 and U2, so all you have to do is integrate those guys so that we can find the U1 and the U2. So put the integral sign here. We found U1 to be a negative integral of y2 times f over Wronskian with respect to x. And a y2 came out to be integral of y1 times f over Wronskian with respect to x. Right? So you can see that here, so this is going to be U1 times, so U1 shows up here, times y1 plus, right, U2 is this integral times y2, right? So that's how they came up with the variation of parameter formula, right? That's it. I hope that this was clear.